So let's move to the next speaker. We will here talk about the large-scale post-seismic gravity changes due to the viscoelastic flow in the mantle from the recent Megathrust earthquakes by Shin-Chan Han.
Shin-Chan Han.
Yeah, I'm sorry.
Thank you. So actually I decided to change my title, basically the topic of the presentation from the post-seismic gravity change to the, in general, time variable gravity change after the recent earthquake. I thought this general, I thought this general introduction of the global gravity change after the earthquake is more useful to most of you. Sorry. Oh, by the way, this is the gravitational potential change after the earthquake, and it is nothing to do with the gravity wave propagation after the tsunami presented in this morning. So I'd like to start by acknowledging the collaborator and this presentation, Ricardo Riva, Ginny Sao, and Emil O'Connor. Also, I have to acknowledge my colleagues at Nancy Goddard, Skalasky, and Dave Rowland, Fred Porridge, and Richard Gross, and Caroline Dominage. Okay, let me spend some time to explain the satellite system to measure time variable gravity. The satellite mission is called the Gravity Recovery and Climate Experiment, called GRACE. The GRACE satellite consists of two identical satellites, exactly the same mass, orbiting around the Earth at the altitude of about 500 kilometers or 480 kilometers. The separation between two satellites is about 200 kilometers, the baseline. They are tracked by the orbiting GPS satellite, and then two satellites tracking each other using the microwave system. So any mass change on the surface or inside the Earth cause perturbation in all those masses around the Earth. However, the GPS tracking has a precision of a millimeter, which is not very useful to identify any time variable gravity on the surface, including some waters on river and channel, or the groundwater change, or the ice mass change, or glacier mass change. In my case, the earthquake induced mass transport. So the precision of the intersatellite tracking between two satellites with a baseline of 200 kilometers is very precise, like 1 micrometer in range. And then when you take the time derivative, you can get, to remove the bias, you can get the 0.2 micrometer per second type of precision. This is currently operating. So you can, this is really fantastic observation, because the baseline is 200 kilometers. Out of 200 kilometers, we are measuring small change in the level of a micrometer. This is currently operating system. And the GRACE follow-on, or GRACE 2, will be launched in 2017. We'll have a laser interferometer, which has 1,000 times better precision. So we are talking about nanometer level of tracking between the two satellites. Any mass anomaly on the surface exerting the gravitational perturbation between two satellites, and then basic measurement for time variable gravity or earthquake deformation study, we are using the intersatellite tracking measurement. Basically, you can imagine that this is a relative velocity change between two satellites. So this is a synthetic example I made for the actually Chilean earthquake 2010. So this is a pure deep slip model. This is Strassling model. So this is the actual ground track. So when a satellite approaches to the anomaly after the earthquake, it has a variation in terms of range rate, which is a relative velocity along the satellite orbit in the level of 0.2 micrometer per second. And then sometimes we use the orbital perturbation data set in terms of acceleration. This is better to understand because this is basically relative acceleration difference between two satellites, which is due to the any deformation on the Earth or inside the Earth. In this case, the deep slip response is like this, and then the pure Strassling response is somewhat different. So basically, these orbit perturbation measurement in terms of relative velocity or relative acceleration is a primary measurement to study the time variable gravity. So I will show you actual example. This is the Tohoku Oki earthquake. And then this is Japan island here. This is the epicenter marked as a red star here. And then a lot of orbital tracks, ground tracks is shown here. So this is the data in terms of range rate, relative velocity, for 2 weeks before the earthquake. And this is the data, exactly the same data set, but the 2 weeks after the earthquake. You can see very large perturbation right after the earthquake. And then if you remove some background change, like seasonal change due to ocean mass variation, atmospheric mass variation, or even hydrology, you can get the residual. And that residual is the observation after the earthquake. And then this is some predicted perturbation using global CMT solution and USGS, the centroid moment tensor solutions. Obviously, the data prefers the prediction by the green, which is a global CMT solution. And then I just described all the, I will call it waveform, which is different from seismogram. Here, this is basically shows the individual line. So basic idea is the data set identifies and then discriminates the true centroid moment tensor solution. This was really intriguing to me to study further using this type of measurement. This is another example after the Chilean Maui earthquake on 2010. During this period, the satellite was repeating. The gray satellite is not intended to repeat, but accidentally repeating. Why? We need a global coverage to get the global gravity field with confidence. But the satellite orbit changes with the altitude. So during this time, altitude was decreased, and then accidentally it was repeating. But that repeat data set is very useful to identify the change before and after earthquake because they are co-located in the ground track. So the green is before the earthquake, and then magenta is right after the earthquake. So again, you can see the coherent pattern with the predicted range rate change, which is shown in a black line. So there's a sudden change after the earthquake. I guess this is a month, 2 weeks worth of data after the earthquake. So why we have a gravitational change after the earthquake? I have published to interpret the gravity observation after the Sumatra Andaman earthquake. So this is the observation after the grace using the 6 months worth of data. So basically, this is 6 months average gravity change after Sumatra end of an earthquake in terms of plus minus 15 microgram. By the way, the precision of the gravity measurement in terms of acceleration on the surface is about 2 microgram with the spatial resolution of 400 kilometers. So after we did the fault here, there's an uplift. Because this demand is so low, so we expect a large seafloor uplift, smaller subsidence. And then the Moho level, because this is footwall is subsiding, so there's the subsidence of the Moho is expected. But if you think this is just the vertical deformation at the ocean bottom, you can imagine the postseismic gravitational perturbation should be positive because of this uplift. But what we observe is a strong negative one. So at the time, I was really puzzled about this, and then I figured out there's a significant density change within the crust and then mantle. When we calculate the divergence of the displacement vector, which is a density change, we were able to explain this larger negative anomaly. So this is the predicted gravity anomaly based on some finite quantum models. So there's a gravity change due to the surface deformation as well as the interior deformation. Interior deformation means the density change due to the divergence of displacement vector. This plot shows the spheroidal mode. This is taken by the textbook here in the chart. This is the temporal scale. This is the spatial scale. And each individual double-sided model. Here is 500 seconds up to the 56 seconds in temporal scale, and spatial scale 1,000 kilometers to 200 kilometers. The long period seismogram constrain those modes within this temporal scale and this the spatial scale. And then the grace, because we are talking about the postseismic perturbation, then we are talking about the integrated effect of all the modes within this domain. Grace has a limitation in terms of spatial scale. So the very small scale spatial variation can be better detected by GPS, ground motion. However, the GPS distribution is not global. Obviously, we don't have any data on the Earth, on the ocean. For example, the subduction earthquake, using the GPS and the INSA ground deformation data set only constrain just half of the deformation. We don't have any data set which shows the deformation under the sea. So even though GPS has a very special, it's very good to identify small scale deformation, it has limited information about the large scale deformation, which can be better addressed by the Grace satellite observations. So sometimes, how do we get the? Sometimes we want a single equation like this express everything. For example, this is the gravitational potential change on the surface. It's expressed in terms of the well-known functions like K0, K1, and K2, which is exactly identical to the excitation function used in the normal mode synthesis. But to represent the gravitational potential, we use the gravitational potential eigenfunction instead of a radial spheroidal eigenfunction or a lateral spheroidal eigenfunctions. And then those factors like S, Q, and P is a bunch of seismic trigonometric function which has information about the fault geometry. This is very, and then we don't have any temporal terms because we are talking about the permanent changing. And then one thing I'd like to point out is we solve this gravitational potential eigenfunction when we solve other eigenfunctions for Rayleigh wave representation. However, we do not really exploit these Y5 eigenfunctions yet before the Grace data set. Because primarily we didn't have any large-scale gravity observations. So the alternative way to represent this potential is this is exactly the same equation as this. But this is very useful for the person like me in geodesy or the gravitational potential analysis person. So basically this gravitational potential change is governed by the series of coefficients like C and S, which has information about the K functions, excitation was here, and then information about the moment tensor component. And then these functions are basically controlled by three different functions, the isotropic function, dipole function, and then quadratic functions. This shows the isotropic, dipole, and quadratic functions evaluated at various depths. The bottom line I'd like to highlight in this plot is the isotropic function changes is very sensitive to depth. The other excitation, like dipolar and the quadrupolar excitation, is pretty much constant no matter what depth you use, no matter the centroid representative of the source is located 10 kilometer or 20 kilometer or 30 kilometer, it doesn't matter. However, the isotropic response is very sensitive to the depth. And then this is a synthetic gravity change, plus or minus 15 microgram, with the basically same source, but at the 10 kilometer depths, and then 20 kilometer depths, and then 30 kilometer depths. The spatial pattern and magnitude is quite different depending on where the centroid is. This is primarily due to the changes in the isotropic response, which is directly related to the dilatation, which is also related to the compressibility or incompressibility. This is the example, Tohoku earthquake. I don't have much of time, but so the grace provided the monthly mean gravity potential coefficients in terms of spectral harmonic coefficients. This is one particular example. At the degree 30 and then various orders. The blue is the original data set. By the way, this is 2002 up to 2012, so almost 10-year time series. Blue is the original data, and the red is fit using the seasonal variation and linear trend and quadratic trend. And the black is the residual. And then the green line is the fit to the black residual data set in terms of step function and exponential decay. You can see, for example, this case. There's a big postseismic jump and then postseismic the decay. You can identify such observations in many other coefficients too, like this one, also this one. So we measure the amount of step, and then try to solve the moment tensor based on the estimated step. And then we constructed the gravitational potential change in terms of a surface gravity change here. Obviously, the solution based on the cosseismic grace-based central and the moment tensor solution are not unique. A lot of solutions, like this is the deep angle shown here. This is the variation of a scalar moment. Many alternative solutions provide equally good fit to the data. However, any solution in the upper mantle, like if you imagine the prim, the deeper source is deeper than 24 kilometer, which delineates the upper mantle, doesn't provide any good fit to the data. So basically, Grace data set constrain the depth range of the centroid representation of the earthquakes. This also same for the Maui earthquake too. As you can see, a lot of a step and then postseismic relaxation pattern, but somewhat noisy because this is smaller earthquake. Sumatra earthquake. This is so obvious. This big step and the relaxation pattern. Big step and relaxation pattern. And then it constrains the centroid representation of the source within the crustal layer only, not the upper mantle. Upper mantle was too incompressible. I'll skip this. Instead of giving a conclusion, I like to open the discussion to use this kind of satellite-based gravitational potential measurement for earthquake study and also the geodetic study. I mean the postseismic the deformation study to inform the rheological behavior of the upper level of the crusty. So this plot shows, this is actually my dream. This is, I call it potential when, actually this is the, from the spaceborne gravimetry. I calculated, this is the 15 minutes after the Sumatran Andaman earthquake. This is 1 hour, 2 hour. This is the permanent change in terms of surface gravity change plus minus 5 microgal. This is prediction based on the summing all the normal mode from gravity mode to 200 seconds, which corresponds to spatial scale down to 450 kilometers. It has the detectability of the grace is 2 microgal at 400 kilometers. This transient signal, this is not seismic wave. This is a potential change after the earthquake during 2 or 3 hours. Possibly those kind of orbital tracking data set may be very useful to even look at the transient deformation after the earthquake. I will conclude my talk here. Thank you very much for your attention.
I'm curious about. I'm curious about permanent changes in relative sea level that accompany the earthquake and how, that would affect the measurements. If that's something important.
Yes, sure. I didn't explain that part here. The relative sea level is changing because of ocean bottom uplift. Also, the sea level is changing in response to gravitational potential changing. But the sea level change due to gravitational potential change is really small. So relative sea level change is primarily due to the vertical uplift of the ocean bottom. So you have to consider, in this case, when you calculate the gravity, there's interaction between ocean and then the crust. So you have to consider the gravity as a density contrast between the crust and then the ocean. However, the ocean effect is primarily due to the sea surface uplift, which causes the relative sea level change. The sea level changing due to gravitational potential is really small. It's not detectable.
One other question?
Very interesting. During my talk, I was asked if a gravitational anomaly could help detect seafloor changes caused by large landslides, and my answer was that I didn't think that this would be detectable. Now you are talking about methods that become increasingly more accurate, but here we're talking about the shifting of a mass, which could be hundreds of cubic kilometers, but it doesn't go all the way to the crust. It's only local in terms of footprint. Now, would you be able to see those kinds of deformations in post-seismic anomalies?
So you're talking, if I understand correctly, you're asking about the accretional wedge effect, or
something like that. Any kind of small-scale seafloor movement, which is not purely the postseismic, large-scale deformation. As far as the postseismic gravity changing, you can see. This is Sumatra Island landscape. You can see, if you believe this curve is entirely due to postseismic relaxation, you can see the level of signal and the level of noise. But that's long term, right? That's many days or weeks.
Right. You're
I'm talking of something that occurred almost simultaneously, perhaps 2 or 3 minutes into the main atom.
Actually, the one of seismometry in Santa Barbara and myself was talking about the detection of the accretional wedge effect after the Sumatra and the Monastery, but we were not successful.
It would be probably something interesting.
That's right. Maybe using the next generation DNS instrumentation.
I think there'll be a question of wavelength.
Right.
Because the landslides are pretty short wavelength, so you're going to have to go to L equals what, 100, 200? And that's becoming difficult, I think.
All right. Let's continue with Shigemuro Yama.